The XV15 tilt rotor program at Bell Helicopter Company is a jointly sponsored research program by NASA and the United States Army. It is a 4-year program which began in August of 1973. First flight is scheduled for July 1976. The objective of the joint venture is to prove through flight research the tilt rotor concept and to determine its applications in both civil and military missions. The XV15 is sized to be tested in the Ames 40x80 large-scale wind tunnel prior to first flight. Bell will design, build, and test 2 identical tilt rotor aircraft. A unique feature of the tilt rotor is its high hover efficiency. 2 25-foot diameter slow-turning rotors provide helicopter-like VTOL performance and handling qualities. In addition, this low disc loading allows successful auto-rotation after total power failure from all flight modes. As an airplane, the tilt rotor has twice the range of a helicopter at twice the speed. Normal cruise speeds of over 300 knots are possible with this concept. In addition to the tilt rotor's VTOL capabilities, it has excellent stow characteristics. By converting the pylons 20 degrees from the vertical, over twice the payload may be lifted from a 300-foot runway. Twin Lycoming T-53 engines power the XV15, giving it enough power to hover above 7,500 feet at its design gross weight of 13,000 pounds. The rotors are interconnected to allow single engine operation in all flight modes. Each engine is mounted in nacelles at the wingtips. The nacelles house the engines, transmissions, hydraulics, rotors, and controls. The conversion axis is located on the aft wing spar. Conversion is accomplished by actuators mounted on the forward wing spar. Conversion or reconversion may be accomplished in 11 seconds. A unique feature in this NASA Army program is the use of the flight simulator for advanced aircraft at Ames Research Center, Moffett Field, California. This large moving base simulator has been used as a design tool in the development of the XV15 tilt rotor. The aircraft's flight characteristics, NASA, Army, and Bell test pilots evaluated the handling qualities of the XV15. Changes to its cockpit arrangement and control system were recommended by the pilots and incorporated in the design to simplify the workload in all modes of flight. Let's now join Ron Earhart, Bell's XV15 project test pilot, in the simulator. Ron will describe the cockpit. He will then demonstrate a VTOL flight at design gross weight, followed by a flight at maximum gross weight using a short takeoff and landing technique. Note the low pilot workload during the conversions and reconversions in the flights.
We're now in the cab of the NASA Ames flight simulator for advanced aircraft, where the final design configuration of the XV15 tilt rotor are being evaluated by NASA, Army, and Bell Helicopter Company test pilots. To the extent possible, the XV15 cockpit layout is mocked up in the simulator cab. Before we go to some flight maneuvers within the capability of the XV15, I'd like to describe the cab for you. This is the main control stick. Operates in the helicopter mode similar to the cyclic control stick of a helicopter. In the airplane mode, it operates in a normal control stick controlling the aileron and the elevator of the airplane. On the control stick is a switch for releasing the force field system, a switch for releasing the stability and control augmentation system, and a force field system trim switch for trimming lateral and longitudinal control forces. Over here is a power lever thrust control device. Operates like the collective pitch control of a helicopter when in the helicopter mode, or as power control lever or throttle when in the airplane mode. On the control stick is a switch for releasing the RPM governor, a switch for locking the pylons in the down position, a beep switch for controlling rotor RPM, another beep switch for controlling the nacelle incidence angle. We'll now move on to some flight maneuvers that are within the capability of the XV15. We're hovering at the VTOL port. I'm turning left to a heading of west for takeoff. We're heading into the wind now on a westerly heading, beginning takeoff. Gear coming up. "60-knot climb, I'll begin converting to airplane. Flaps coming up. Locking the pylon, decreasing rotor RPM to the airplane setting. We're now accelerating to the 260-knot airplane cruise condition. Now we're at 260 knots, decreasing to cruise power. We're now in the airplane configuration, cruising at 260 knots. I'm lowering power to slow down for conversion back to helicopter. Beeping RPM up to helicopter operating RPM. Flaps coming to 20 degrees down to help decelerate us. Unlocking the pylons. Dropping flaps further to 40 degrees. And beginning to convert back to helicopter. Lowering landing gear. We're now in the helicopter configuration. I'll be losing altitude and slowing down to begin an approach into the VTOL port. And we're now at a hover over the VTOL port. We're now on the end of the STOL runway, preparing for a STOL takeoff where we'll use 60 degrees in the nacelle incidence angle. I'm starting to beep the nacelles over now to 60 degrees. We're accelerating down the runway. Rotating for liftoff. Gear coming up. I'll be converting forward now to airplane mode slowly. We're now converted to the airplane mode, climbing at a climb speed of 150 knots. We're now converting from the airplane mode to the STOL approach mode, 60-degree nacelle incidence angle for an STOL landing on the STOL port ahead of it. Converting back to 60 degrees, pylon angle now. Landing gear coming down, flaps coming to 75 to help steepen the approach. intercepting the glide slope. Beeping pylon back to help decelerate us. We're on the brakes.
In addition to handling qualities, performance and emergency procedures were tested in the simulator. Successful auto-rotations were made from simulated total power failures at speeds up to 300 knots. The simulator has proved an invaluable tool in the design of the XV15. The tilt rotor provides basic advantages over the helicopter while maintaining excellent low-speed flight characteristics. With long range, high speed, low noise, and low fuel consumption, the tilt rotor rivals the turboprop airplane in productivity without the need for runways or airports. This aircraft promises a new era in aviation. Its unique capabilities will open up new horizons for missions not yet conceived. With economical and fast point-to-point transportation capability that is second to none, the tilt rotor will revolutionize the aviation community and alter commercial transportation and military tactics in the late 70s and early 80s.